For a linear transformation from Rn to Rn, we can always use a matrix multiplication. When we switch basis from standard basis to some other basis, the matrix representation, that A, will also change. This is this concept of similar matrices. The A is represented by this M, P inverse AP. You could also do some matrix algebra to connect them in this way. So in the previous video, we had an A. We chose to switch into this new basis. And when we made that switch of basis, the representation of A became this new simple matrix, a diagonal matrix. Is there a change of basis that will make A look as simple as possible? And the answer to this is yes. We're going to choose eigenvector basis. But let's take a look at it in a general way. So let's say that A is an n by n matrix, and let's assume that A has an eigenvector basis. Now, in a previous video, we talked about some conditions that will lead to A having an eigenvector basis. Essentially, you have to have enough eigenvectors. If you're in Rn, you need to have n independent eigenvectors. If I give you any single vector in Rn, I will always be able to write it like this. Because this is an eigenvector basis, any time I apply the matrix on one of those eigenvectors, it will simply return lambda times that eigenvector. So we are going to apply A to this matrix representation. So we are going to take this basis representation of A and write it like this. We're going to apply linearity of matrix vector multiplication, and this is going to allow us to write the following: C1 AV1 all the way down to Cn times AVn. And the whole point of doing this is that we now get to apply the eigenvector definition. We'll get C1 lambda 1 V1 all the way down to Cn lambda n Vn. We've got this scalar in front of vector v1, and in front of all of these things, we have a different scalar times this vector vn. There's a matrix that holds all of these basis vectors times a certain vector that holds the weights, c1 lambda 1 all the way down to cn lambda n. This is a matrix P, and this is going to be the representation of that vector in our new basis. Now I'm going to focus in on this part right here. This is a C1 lambda 1, C2 lambda 2, all the way down to Cn lambda n. This may be tricky for you to see, but you could represent this as a diagonal matrix that has all these eigenvalues down the diagonal times these weights. This is 0 and 0. You can represent a matrix A in a new basis with this relationship right here. The new representation is P inverse AP. If we choose an eigenvector basis for Rn, that will tell us that A, our matrix of our transformation, will be similar to a diagonal matrix. That was exactly what we were looking for. If I switch to this special basis, it'll make my matrix look very simple. But are there any other options? Is eigenvector basis the only basis? Is there any other way for me to get a diagonalized similar matrix? So let's just forget about everything else we've talked about up to now. So if I want a diagonal matrix to be the result of this change of basis, I can multiply both sides by a P on the left. What does P have to be? What does D have to be? And then I'm just going to use the definition of a matrix times a matrix. So on this side, what I'll have is A times the first column of P all the way down to APN. We're going to assume that all of these matrices are n by n. Now on the other side here, let's say we have P1, Pn. If this is a diagonal matrix, that means there's some constant down this diagonal and there's zeros everywhere else. By matrix definition, I'll have P times this first column all the way down to P times this last column. And on the other side, I'll have an AP1, APN, just by matrix definition. if I were to take a look at this particular product, this just says pick out the first column of this matrix here. First column of this matrix here is just a P1, so I'll get a D1, P1. The second entry will be a D2, P2, and this last entry will just pick out the last column. If I'm interested in saying, hey, look, if I want to be similar to a diagonal matrix, what this is going to require is that for the first entry of this matrix, it has to be the first entry of this matrix. AP1 has to be D1, P1. And if we continue this down the line, what we get is the following. This is just the definition of eigenvalues and eigenvectors. Remember that if you have a matrix P and you want it to be invertible, it can't have any 0 rows or 0 columns. So all of those vectors are non-zero. And so the point is this. If your matrix A is similar to a diagonal matrix, P has to have eigenvectors of your matrix. These all have to be eigenvectors, and this diagonal has to be the corresponding eigenvalues. This leads us to important definition. We're going to say that a matrix A is diagonalizable if it is similar to a diagonal matrix. If you are similar to a diagonal matrix, that means you are able to write this as A equals PDP inverse, or you can write this as AP equals PD, or you can write this as D is P inverse AP. If a matrix is diagonalizable, there's a change of basis that will allow you to represent it as a diagonal matrix. What has to be true in order for that to be the case? A is diagonalizable if and only if. That means there's only one way to do it. A has an eigenvector basis for Rn. Note that diagonalizations are not unique. In the previous video, I showed you that this matrix has two distinct eigenvalues. You can verify for yourself that there are indeed two independent eigenvectors, and that means you will have a diagonalization. But there isn't just one diagonalization. You can have more than one. You could choose P to be V1, V2, D to be 2, 0, 0, negative 1. Or you could say, well, I'm just going to put them in different orders. V2, V1, D2 will be negative 1, 0, 0, and 2. So the key to understanding diagonalization is that you are switching into eigenvector basis for your matrix.